All right, hello everybody, and welcome to today's session. Um, I'll be talking today about implementing IoT device remote control using a Raspberry Pi. I hope you can see the presentation. If not, then please let me know. You should see the Zoom toolbar. And if you have any question during my talk, you should see like the questions and answers button. So please click on it and type your question. I should be able to answer that. So I can answer that in line or at the end. So first, let me give like a quick agenda of today's talk. I'll give a quick introduction about myself. I'll talk a little bit about the hardware that I'm going to use in the presentation, because today's presentation will be pretty much a hands-on session. And then I'll go like and explain the implementation that I'm going to use. And then at the end, I will run the questions and answers, the Q&A. All right, so let me start. So first of all, who am I? Who you're like listening to? My name is Sergey, and I'm an engineering director at Tesanta. Tesanta is a software development company founded in Dublin, in Ireland, in 2013, so 10 years ago. And we are making network software for embedded systems. So I'm an original author of Mongoose Embedded Library. So the link is given here. So and this library is something that I'm going to use later on, like in this presentation, pretty much exclusively. Let me give a couple of words about this library, because that's important. So this is a Swiss Army knife for embedded networking. So this is an open source library, and it consists of two files, mongoose.c and mongoose.h. And these two files implement the whole networking stack. So if you want to implement networking on some embedded device, being it like RP2040, some other microcontroller. So the only thing you need is just to copy these two files to your source code, and that's it. So you don't need anything else. You don't need a separate TCP/IP stack. You don't need drivers. You don't need anything. And soon you will not need a TLS library as well, because we are going to embed the TLS 1.3 implementation inside. So also, I'm an author of the bare metal programming guide. It's also published on GitHub. If you search GitHub for bare metal programming guide, the most popular one is the one. So with more than 2,000 stars. And if you're a junior embedded firmware developer, or even not the junior, I highly recommend going through this guide, because it talks about the bare metal programming, starting from the very basics, like setting, getting bits in a register, like what is the memory layout, down to very advanced topics like running networking, implement automatic testing on embedded devices, and so on. So yeah, highly recommend this one. And by the way, it was recently published by the Electro magazine. So I'm also a speaker at various conferences like Embedded World and others. So basically, I have like a pretty good understanding in the field, and decades of experience in this embedded networking area. So Well, and now let's get down to the meat of the presentation. So what I'm going to talk about today, I'm going to talk about how to turn your Raspberry Pi Pico into remotely controlled device, right? So that's the topic. And the hardware that I'm going to use is the standard Raspberry Pi Pico board with the Ethernet module from Wiznet, and which is shown on the slide. And by the way, let me stop presenting the one slides. Let me start presenting the whole screen because I want you to see the entire screen. So because I'll be doing stuff and you need to see that. So let me reshare the whole desktop. So now I'm sharing my whole desktop. You should be able to see it. If not, please let me know. So what is the goal? The goal is to show how to turn the like standard Pico into a remotely controlled device. And I'll be doing that by embedding Mongoose library into it and implementing MQTT client that talks to the public MQTT server, and then implement the remote procedure call, like so-called RPC mechanism over the MQTT, so that you can send commands remotely to your board over the MQTT server, and then get responses. So this is the goal. And like, first of all, let's talk about the hardware. So as you can see, I have like this this Pico connected to my workstation, right, with this module, and basically there are ready to go modules, like ready to go boards like this with the already integrated module, but I didn't use them just to show, like, to use a standard one that like any of you can build yourself. So and by the way, everything that I'm going to show here would apply to pretty much any other microcontroller, because this specific module, this Ethernet module from Wiznet, it provides an easy-to-use serial interface, SPI interface, to read and write Ethernet frames from the network. So that means that any microcontroller with SPI interface is able to use that module, so is able to receive and send frames from Ethernet. And if you add Mongoose library to your project, then the Mongoose library has an embedded TCP/IP stack, so it can handle those frames and provide you a high-level interface to create connections and send receive data. So that's the whole idea. So the bottom line is that you can easily turn your, like, pretty much any microcontroller with more than, say, 8 kilobytes of RAM to a networking device using this hardware module. So but to spare me some typing, I'm going to use a pre-built examples that are already exist in the Mongoose repository. And what I'm going to do, I'm going to explain you, like, all the steps like bit by bit, so you understand everything, so how things work, right? So first of all, let me go and copy clone the Mongoose repository, right? So if I go and just click on this GitHub Tazanta Mongoose, go to my terminal, and I do git clone this repository. So I'm cloning the repository into my home directory. And in the repository, there are plenty of examples. So So if I go to Mongoose and go to examples, there are like many of them, and this is just the like many of those directories are root level directories. So for example, if you go and see examples for STM STM32, like there are many more examples for this specific hardware. So but one of the important examples in the repository are the Mongoose dashboard, the web dashboard, and the MQTT dashboard. So two examples, and those examples they represent the ability to turn the device into a web server. And the second example, MQTT dashboard, shows an ability to turn a device into remotely controlled smart device, right? So and the paradigm to build networking application using Mongoose library, which is, by the way, I could highly recommend to any networking application. So if you use and if you create networking applications on embedded devices, I highly recommend building that application on the workstation, right? So build all networking functionality on the workstation. So to say, create your device emulator, right? So mock all your hardware calls and build on the workstation. And once you've built it and debugged it, tested it, maybe even you can hook it up to the CI, continuous testing environment. Then after that, you can just move the created networking functionality onto embedded device. So this is the paradigm we constantly use in our own development. We highly recommend it to our customers, and I highly recommend it to you. So if you forget everything that I say today, and just remember this one thing, I think that would be the most useful tip that you can take out from my talk. Right. So, and I can show you how that works in practice, this paradigm. Right. So, for example, let's go and go to device dashboard example. Right. So this example shows the embedded device dashboard. Right. And I can see somebody raising hand. So. Not already. So so this is the device dashboard, and as you can see, there are a few files here. Mongoose.c and mongoose.h is a networking engine. Net.c and net.h is the implementation of the networking functionality. So in this case, the device dashboard. And pactfs.c is just the packed UI files, right? So if I type make in this directory, it starts an example on my local workstation, right? On port 8000. So if I go to port 8000, I can see the device dashboard on my screen, and this device dashboard is running on my workstation. But now, if you go to the directory called RP2040 and to directory Pico W5500, so and you see what's the content of this directory. So the content of this directory is pretty much the same as the content of the workstation directory. So it has file main.c. And it has a mongoose.c and mongoose.h, which is a networking engine. And it has the net.c and net.h and pactfs.c, which are symlinks to device dashboard files. So as you can see, these files are one-to-one, not a single change, it's just a direct copy of the workstation file. So that demonstrates the principle that I told you before about. So that networking functionality should be developed on the workstation and then used one-to-one no, not a single change on your embedded system, right? So let me build it, and let me try to even flash it. So make flash. So I build it, and as you can see, if I look at the examples, RP2040 Pico W500. So in the main.c. So what main.c file here uses? So it's a very simple file. So it's like about 100 lines of code. And this file implements the dashboard that you see here, right? So on the screen. So what it does, it initializes it's a standard Raspberry Pi Pico RP2040 firmware using C SDK. So what it does, it initializes the LED pin. It initializes the USB output. And then it initializes the Ethernet pins. So you can see Ethernet SPI in it. So which is actually just sets up SPI to use this W5500 module. And then it initializes Mongoose, and you can see basically this is the whole Mongoose functionality. So it initializes the event manager, then initializes the built-in network stack. So it says, like you have an interface. This is your MAC address. So we get MAC address from the unique ID of the Raspberry Pi board. So we say, okay, please use the built-in driver for W5500. And then start the TCP/IP, initialize the built-in TCP/IP stack, add the timer to blink LED. So you can see this LED blinks because like every blink period MS, which is 1000 millisecond, it blinks. And then it just goes and falls into it. It calls the function web init, which is defined in net.c, which implements this web dashboard, and then it falls into infinite event loop. So that's the way it works. And as you can see, it's a very simple. It's a bare metal firmware. Well, actually, yeah, it's a bare metal firmware. So, but this piece of code, initializing the networking and running the event loop, can be used and can be run under the RTOS as well. So the same code will run in whatever OS you might use, like FreeRTOS or Zephyr or Windows or Mac. So it does not really matter. So Mongoose runs on everything, and it runs the same way. So the API does not change, right? So that's basically the functionality. And let me see. So okay, so I have this this board flashed. Let me run the terminal program just to see the output. Dev cu USB minus speed 115200. So minus speed dev USB cu USB minus speed monitor. Okay, so this is the output from the board, so I can see the IP address that it got from the HCP. I have a question. So Roy is asking, why does the for loop uses a 1 millisecond pull rate at not 0? Well, the thing is that when we use the bare metal bare metal implementation and the embedded TCP/IP stack, this second parameter is really at the moment is just ignored. That doesn't matter what we put here, 0, 1. It could be even like int max, right? It does not really matter. So this poll function, what it does, it runs the one iteration of networking poll. So it basically looks for frames on Ethernet. So did we receive anything? And if we did receive the frame, so the TCP/IP stack goes and extracts that frame. It looks okay. Does that frame belong to any connection that I already have? If it does, that it extracts the payload and adds that payload to the connection and calls the event handler function for this connection, right? And then the event handler function, which is written by the user, it can send some data back, right? So and basically the spool function then looks, okay, do I have some data, written by the user that I need to send? And if yes, then it goes and gets the data and then splits it into frames and sends back to the user. So that's basically how POL works. And the same way it works under Windows or Mac with the existing TCP/IP stack. It just uses socket interface to get and receive data, not the low level, frame interface, like low level driver interface. So that's how it works. And as you can see, so if I get this IP address and type into my browser, I get the same UI that I get for the workstation, right? No changes, absolutely no changes. It's the same UI, but it runs on an embedded system, and you can see, you can see this principle in practice, and I highly recommend you doing the same, right? So basically, the idea is to get the all networking encapsulated in a single file, net.c, and provide the interface in net.h. So this is the interface. So this specific interface, it exports only one function, web init, like initialize this web UI. And if you take a look at this web init, that it does so this function web init, it just initializes Mongoose listeners using this event handler function, and then this event handler function for the web UI, it implements like a bunch of RESTful calls, like to manage the device. So you can do you can save settings, you can load settings, you can update the firmware and so on. So, but now this is all good and nice, but this is web UI. What I wanted to show you is the like MQTT way, remote management. Because right now, what is the problem with the web UI? If you implement web UI on your device, you can access that web UI only locally, right, from the local network. You cannot use it from anywhere on the internet because it's a local listener. So you should do something with your network settings to to export your listener, your device, to the outside world, to the listener, your device. You should expose it to the internet, and that's very dangerous, because once you open up your device to the public, it can be taken down very easily, because running like network services on an embedded device is not really recommended from many perspectives, right? Security, resources, and so on. So it's really easy to denial of service the embedded device, because it has so little resources. So it's not recommended, even if you run the web server on your local network. You probably don't want to expose it to the public, right? So what to do if you still want to access your device remotely? So what is the solution? So the solution is to let your device to connect out, to work as a client, not as a server. So, and if it goes and makes a connection to the server, to some like internet visible server, and then you make that internet server to kind of relay data from your client to the device, then that would work nice, because the device, the something that handles the connections could be a powerful internet server with a lot of resources, with the protection you could put in place, right? And your weak, way less powerful embedded device is just a client. It does not expose any network port, so it's like pretty safe from this perspective, from the security point of view. It does not expose anything. It just makes an outbound connection to the remote server. So, and there is a standard protocol for that. It's called MQTT, right? So MQTT servers and MQTT protocol is designed for exactly that, right? So that embedded devices can do an outbound connection to the MQTT server, and then they use a publish subscribe mechanism to get to exchange data, right? So MQTT client connects to the server and says, okay, so I want to publish data on this topic, right? And they can write data, and other clients can say, okay, I subscribe to this topic, and any client that publishes data on that topic will be that data will be relayed by the MQTT server to that device. So this is a very, very simple mechanism, but it allows embedded devices to be remotely visible without any non-standard tricks like forwarding web and stuff like that, right? So it's a standard protocol. So and that's what we're going to use. So Mongoose library provides not only web dashboard example, but the MQTT dashboard example, right? So let me show you where it is. So, and we're going to use it. So if we go to examples and search for MQTT, where is that? MQTT dashboard, right? So, and that MQTT dashboard contains of two files, it has two files, a client, right? So this is a client, which represents a device, right? And again, it's like a really, sorry, the client, it represents the dashboard, the remote dashboard. And we have a device which represents a device. And as I said, the functionality is implemented in two files, net.c and net.h, right? And now, since this client has built in this paradigm, encapsulating everything in a single file, what we can do, we can just reuse that net.c and net.h in our embedded example, and that's what I'm going to use, and that's what I'm going to do. But before that, I want to run the dashboard, the MQTT dashboard. So if I go to, let me start another terminal. So if I go to CD Mongoose examples, MQTT dashboard, and client, right? So and if I run it, so when I type make, it runs a Mongoose web server in this directory, in this client directory, and it runs a really simple P-React application, right? So it starts, I think it starts also on the port 2000. So this is an MQTT dashboard that it runs locally on my workstation. So this MQTT dashboard connects to this connects to this MQTT server, which is a public server. It's a public server called HiveMQ. So this is some public server running by some German company. And anybody can use it, this public MQTT server. And this is a kind of a client that you can use, a web client. So you can connect to this server, you can subscribe to topics, and you can publish to topics. So you can see what's going on, right? So this is the idea. And basically this MQTT dashboard, what it does pretty much the same. It connects to this MQTT server, but also it expects some devices to to exchange the information on this root topic, which is specified here, right? So and this is what devices in this directory. So in this directory, cd mongoose examples MQTT dashboard device. So this is what this kind of device does. So if I run make to run a device kind of emulator on my workstation, so you should see that, okay, so I've got a new green device that is connected. So I click on that and you can see that there is status online, there is an LED, kind of a control, like some simple control, and a firmware update mechanism as well, right? So that's what this MQTT dashboard implements. And as you can see, now I am running everything from my workstation. So I did not even touch yet an embedded device. So I ran this MQTT dashboard from my workstation, right? So it runs here. And I also ran here in this window a device emulator, which also runs on my workstation, right? And you can see like how that works. So and let me show you how it works kind of like from the MQTT point of view, and then I'll talk about how it's implemented in the code so you understand how it works, right? So let's go to the MQTT dashboard, or maybe I'll do like vice versa. First I'll go and show you the code of this MQTT client on the device side, so you understand how it works. And then I'll show you on the MQTT side what stuff the dashboard receives and sees in order to implement this UI, right? And by the way, this UI is implemented using a library, like a public library that is able to speak MQTT protocol. So this UI basically connects to this MQTT server, and it just understands the devices that speaks that speaks that language, so that we implemented. So let me do that. So if I go to examples, MQTT dashboard, and open the file device main.c. So this is the file that implements the whole functionality. Oh no, basically that's the file. That's just the driver. So device main.c is just the driver. It initializes Mongoose library and falls into infinite event loop, right? The meat of the functionality is in net.c, and the functionality is exposed, the API is by net.h. And as you can see in the net.c and net.h, what we expose two functions like web init and web destroy. It's kind of like, like start networking functionality and stop networking functionality. And there are two mock hardware functions like GPIO write and GPIO read that are required for this, like to mock this device panel, like LED pin and LED status. So you can set the pin and set the status. And as you can see, this mock in main.c is very, very simple. So we just mock the pins using an array of 100 virtual pins. If we got a write call to certain pin, we just set the status to the status that we told. And if we read, then we just give back the status from the certain pin. So it's a very simple hardware mock. So this way our workstation mocks the hardware. So I can change the LED, like for example to, I don't know, 42, and then click on a LED status, like I can set it and set it on and off, and all that will do, it will just call these two functions that basically just set the Boolean variable. But the meat of the functionality is in a file called net.c. That is the function that implements the whole networking functionality on the device side. And as you can see, it's a file of like 250 lines of code roughly. So, and what it does, so let me like guide you through this. So what it does, this piece of functionality, first of all, it sets up, so it has some static variable or device config, right? So it emulates a real device and sets and has a static variable saying my config is this, and it has LED status, LED pin, some mock variable brightness, which we can set here, and a current log level, right? So that's what it does, and pretty much all of that is mocked, right? So LED and brightness is all mocked. So and this function generate device ID, it generates a new unique ID on every run. So that means that if I stop this application and run it again, it will appear as a new device, right? So if you want a stable IDs, you shouldn't use this randomly generated IDs. But right now, like this functionality uses randomly generated IDs, so be aware about this, right? And then what then we do next? We create an RPC service. So a Mongoose library provides an API to create RPC functions, JSON RPC functions. I think you should be aware about what JSON RPC is. If you are not, is a standard protocol that lets you turn anything, right? Anything into a server or client, and you can send a requests and responses using a standard format as a JSON formatted strings, right? And the format of the string is really simple. It has an ID field, it has the method field, and parameters field. So basically, you on the server side, you receive a JSON string saying ID 1, method reboot, parameters 500. And you can interpret that as reboot after 500 milliseconds, and you make a response ID 1, like you respond back the same kind of request ID. And then you can say a status, okay, so a result, sorry, not status, result true. So you've got it, and you'll reboot after 500 milliseconds. So that's an example of JSON RPC communication, and it's standard, and you can implement it over any carrier protocol, over serial port, over plain TCP/IP, over WebSocket. And here the implementation is over MQTT, right? So what this implementation, what this client is basically a JSON RPC server over MQTT. So MQTT protocol provides it's a framing protocol, right? So every message is a frame. So in our case, we treat every frame as a JSON RPC string, right? And MQTT protocol is a publish subscribe. So any client, it can subscribe to a certain topic and publish to a certain topic. And that basically represents, it works kind of like a serial interface, TX and RX. TX is the published topic, and RX is a receive topic, right? So basically, our device, what it does, you can see this line. There is a timer. Every 3 seconds, we call a function timer fn. And this function timer fn is a reconnection function. It says, okay, so if the global variable connection to the MQTT connection to the cloud is null, is 0, that means we are disconnected, then we create kind of like a message saying our device, like our root topic, which is this topic mg device / our ID, which is randomly generated / status. So we publish this message to the MQTT server every time we connect to it. So we say we basically report our status on every connect. And what we report, so again, this is a Mongoose library API, so we format the, Mongoose library gives you an ability to print JSON, to generate JSON, and to parse JSON. That's what it makes it so easy. So we basically say method status notify. So that is a JSON RPC topic, like the notify method. And as you can see, we do not pass an ID. So every JSON RPC string without an ID, it's a notification. That means the response is not required. If you send an ID, that means that you want response from the server. And if you do not send an ID, you just notify it. You just say, okay, so this is the function to call, but don't send me a response. So this is exactly what it is. We are sending the notification on the status topic, and we are sending parameters like status offline. So what is this? This is a so-called keep alive sorry, not keep alive, how it's called, well, last will. Yeah, it's last will. So MQTT has a quite useful and funny feature. When you connect a client to the MQTT server, you can set a parameter in a connection message saying, when I'm disconnected for whatever reason, maybe I could be killed, or I cannot even know what would be the reason for this connection. But if I'm disconnected for any reason, please send this message to this topic. So it's basically will be the responsibility of the MQTT server to send this will message. So basically what we are saying is that our device says, when I'm disconnected for any reason, please send an offline message to this status topic. So mark me offline. That's basically what it is. And then we prepare the options, MQTT options, and we say, like the version that we're going to use, it's like 3.1. We say retain. So retain, that means that like it's kept even after we disconnect. And then we send this, we connect to this MQTT server. So basically, this piece of code is a reconnection logic. If we get reconnected for any reason, we connect again, right? So this is the function that we call like MQTT connect. We use the URL, which is this MQTT server URL, -MQ. And the most important thing in this call is the FN, the function, the event handler function that Mongoose calls on every networking event that happens. So this is the root, this is the meat of this whole client. So this is the meat of the networking functionality of this client. This is an event handler function. So this function receives 4 parameters: a connection, event number, event data, which depends on the connection, on the event number, and the pointer that is passed to the connect function, right? So and we see that there is basically a switch statement, right? So if we just if we created the connection, we just log this thing. So we are created. If we connected to the MQTT server, that we print that we are connected. On any error, we just print that error. If we successfully handshaken with the MQTT server, so if MQTT server authenticated us, then we call a function subscribe and we publish our status, right? So the function subscribe, it's subscribed to the, RX topic. So that's very important. Every device has its prefix, which is this root topic / device ID, which is this random number, right? Or sorry, random string. And then every device subscribe to this kind of prefix /rx. So it listens to the rx topic for its own ID. And basically, if you send messages, if you send JSON strings to that rx topic, then it will receive it. So device will receive it. It will receive that this message. It will treat it as a JSON RPC string, and will handle it using JSON, using the using this JSON RPC server that we configured here, right? So, and this configuration of the server says, okay, so I register this methods config set, OTA commit, device reset, OTA rollback, and OTA upload. OTA services that they are used for firmware update. And this firmware update actually works for certain microcontrollers, for certain lines of ST and certain lines of NXP controllers. It works. And right now we are working on support for Raspberry Pi. So very soon the this over-the-air firmware update will work also on the on this RP2040 boards, right? So so this is pretty much it. So, and we can look at the example, for example, RPC device reset. Let's see if we get the request to reset, then we call this function, like we add the timer to reboot after 500 milliseconds. And you can see other functions are implemented in a similar way. So for example, if we save the config, we expect a JSON RPC string with params. We fetch parameters from the past JSON string, like LED status, params brightness, params LED pin, and then we apply those fetched parameters to the static config, like as device config, LED pin equals TMP pin, right? So basically that's how it works. We get a JSON string to set the config, we fetch the past parameters and apply to our static in-memory configuration. So that's how it works. And you can implement other RPC function. You can easily extend this RPC API by adding your own management functions, right? So and let me go back to the event handler implementation. Where is that? So yeah, here it is. So when we connect to the MQTT server, we subscribe to this RX topic. And when we've got a message, right? So when we've got a message from the MQTT server, that means somebody sent us a JSON string on the RX topic. Then we basically run this RPC API call, MGRPC process. It will parse the incoming RPC JSON string, look what the method is. It figures out, do we have this method registered or not? If we don't have it registered, it replies straight away that, okay, I don't know what is this method. If it has this method registered, that we call this MGRPC process calls the handler for this method. And as you can see, we pass the kind of like the way for the method to print the response. So we print into the local IO buffer. So, and then if we see, okay, so if the local IO buffer is filled, then we publish it, we send it back. We change the status, we notify of the status change, and then we just, destroy this local IO buffer. So that's pretty much how it works. So in a sense, when we get the message from the MQTT server, we treat it as the RPC request. We handle it, send the response. That's it. And when we get a close event, we set the connection to null, like this, a static variable connection to null, and that will trigger the reconnection timer function. After every 3 seconds, it will try to reconnect again. So this is pretty much it. That's how it works. So, and as you can see, the real kind of device logic would be hidden in the RPC process, like in the implementation of your RPC server. And this implementation, by the way, it's pretty much independent of the protocol. So you can define this set of RPC functions kind of like, they are absolutely don't have any clue like what is the what is the carrier protocol. All they know is that I've got this string, this string request, and I can print a response using this print function. That's all. Like and you can have the same RPC server served over many endpoints, like over many physical kind of connection types, over Bluetooth, over BLE, over serial, over HTTP, over WebSocket, and over MQTT. And by the way, we have implementations like that, like exactly like that. So it's quite useful, for example, to define an RPC implementation that configures your device. And then you can export that to a local HTTP and BLE, right? So that you can configure your device using the phone app, or by like running the like local access point and configure through the access point. So and then you can expose the same interface over MQTT, right? So then when you have your device configured, you connect it to your private MQTT cloud, and then you can still be able to reconfigure your device over MQTT using the same RPC mechanism. So it's really very, very like powerful technique. And yeah, like we are using Mongoose library because it implements that all, but it does not really matter if you're not using Mongoose, you're using something else, you can still use the principle, right? So now I think you understand how all stuff works, right? And what I'll do here, I will show you how it looks like from the MQTT a server perspective, right? So I will use the MQTT WebSocket client, and let me subscribe to the topic. Like, let me subscribe to all messages from this topic MG device, right? So I've subscribed to all of it. And as I subscribe, you can see I immediately get a lot of stuff. I get a lot of stuff from different from different topics, and you can see, probably you cannot see because it's like pretty dim, different kind of device IDs. So these are devices that are already disconnected, right? And this is one online device that I have connected. And if you compare that to this dashboard, they match, right? So that's what this dashboard did. It connected, and the MQTT server immediately sent this this message, because the topics were marked as retain, and yeah, so that's what dashboard saw, right? So, and now what we can do, we can take this online device and send some RPC commands to that device, right? Let me do that. So this device, let me copy the device ID, right? So I go and I publish to the topic. This is the device ID I should use, and the RX, right? So the topic RX is the one that should get the data, right? And let me first send some garbage like ABC or hello. So if I send hello, then I get the error to the TX topic, right? So this is the response topic. I get like standard JSON RPC, like this is the request, this is the response, and this is the notification. The notification basically said like nothing has changed. So but now I can send the real like formatted ID one, formatted JSON RPC message, like method hello, for example. It will as well send me the error saying like message like method hello not found, right? So but I can send something that exists, right? For example, one of the registered methods, Like I can send device reset, right? So I can say device device reset and publish. So and I see the result okay, right? And yeah, so device has been reset. But I think, yeah, I think this device reset is, is also mocked on this Raspberry Pi, so it didn't really reset in reality. But it definitely, if you can look at the implementation, that it calls, yeah, it calls this method ng device reset. So it just right now for Raspberry Pi it's mocked, right? So this is the idea, and let me show you if I get the dashboard, if I snap the window out and run this console, and if I check the toggle button on the dashboard, let me check it. So you can see what messages has been sent. So we changed the LED to status to off, and basically called the status set, like settings set. So that's what we did. You can see we called config set, and we set LED pin 42 and LED status to false, right? And the board responded, yeah, I set it to false. So we called our mocked function. So that's, I think that should give you an understanding how this thing work. So how this device kind of client works from the device side and from this like dashboard side. And now what I'll do, I'll just implement the same client on my Raspberry Pi, right? That's what I'll do. So let me do that. So right now, as you can see, the net.c and net.h, they point to the device dashboard implementation, which is a web UI. And I don't want that. I want to repoint it to the MQTT dashboard instead, right? So I do ln-fs, like change the symlink to MQTT, sorry, MQTT dashboard net, sorry, device net.c to here and net.h to here, right? So now net.c and net.h, they point to MQTT dashboard, not the web dashboard. And yeah, let me see what happens now if I go and rebuild the application. So I'll do make flash, and I think I should, yeah, let me kill the build directory. So sorry, make build flash. So now I'm rebuilding the whole application. I think it should give me the error because the net.c and net.h, they call hardware mocks called GPIO read and GPIO write. And I did not implement that. Yeah, that's it. So you see net.c, it implements this interface, GPIO read and write, which we did not implement. So now we have to implement this. So instead of our mock, we should really implement these two functions and using real GPIOs, and our dashboard will work for real GPIOs. So let's do that. So GPIO write and GPIO read, right? So we should use functions like GPIO read should use functions GPIO get, return, GPIO get out level pin, and GPIO put pin status. So I think this is pretty much it. So we implemented these two functions using Raspberry Pi API. And now I think we can rebuild this stuff, like make flash. And now our device should work. Okay, so one more thing. I think our timer function now blinks the LED. Let me disable that blinking. We don't want it blinking while we are setting and resetting. So now you see the device. Sorry, the device does not blink, right? And here's our dashboard. And now let me flash it again. And let me refresh the console. So now on the console, you see there are two online devices, right? So first online device is the one that we are running on the workstation, right? This one. And the second online device is the device that we are running on our, this one, on the Raspberry Pi, right? So, and let's see which is which. So the one device starts with Y is the workstation, and this one is the real Pico, right? So this is a real Pico device. And now the built-in LED is 25. So if we change the pin to 25, and now if we set it, or like it got offline. So where is that? Oh, here is this one. So when I reflashed it the second time, it changed the ID again, right? So let's change the pin to 25 and set it. Here, you see, so now when I'm clicking the LED status, it sets the pin, right? It sets the pin on a device. So this is pretty much it. So that's all I wanted to show you. How to turn a device into a remotely controlled device using MQTT and JSON RPC, and you can use this handy MQTT UI dashboard. You can extend it. It's all, it's all published. After this webinar, I circulate the follow-up letter email with the references, with slides, with the points to projects, implementation, and you can play it yourself. You can change, enhance it, and you can take this implementation of MQTT dashboard and the device client as a skeleton, as a reference application for your own project. Right. So that's pretty much it. That concludes my presentation. I hope that was useful and you learned something new in it. And please ask questions if you have any. So I already have like one question. So question from Roy. I've been using a WireGuard to forward my local home lab to a VPS. Would WireGuard fit and run on a microcontroller? And is it something Mongoose might support in the future? That is a good question. So WireGuard, I'm not familiar with the WireGuard, but I think it's it's some sort of like a binary, maybe for Windows or Mac that does this forwarding. So, and that's I'm not familiar with this application, what exactly it does and how it works. But my assumption, if it runs on the workstation, it's pretty unlikely that is going to be running on the embedded device, especially like on the RP2040. Most of the applications that run on the workstation, they will not compile, that will not build on the microcontroller, like the vast majority of them. And Mongoose library is one exception. As I've demonstrated here, is that if you build an application using Mongo's library on the workstation, it will work also on the embedded client. But the question is really, so you want to export, you want to publish and expose your your home, your private network, like to the public. So it's kind of like resonate with what I was talking about, running servers and clients. So it's basically why MQTT protocol was invented in the first place, right? It was invented by who was it? Like, was it IBM who invented that? I think it was IBM, some big company. They invented this protocol for their like low power sensors. So they wanted their sensors to publish data using like really low footprint framing protocol. So and that's why they invented that in the first place. So Roy says WireGuard is a lightweight VPN protocol, or like OpenVPN. Yeah, so yeah, that's the question is really about the WireGuard. I have no clue about WireGuard, and does this Open VPN implementation works on the RP2040? Like my guess would be no, but you can check it out. So like chances are it doesn't work on RP2040. But with MQTT, the point is that you don't need VPN. That's the point. So as soon as you have access to the outbound access, you don't need inbound. That's the beauty of MQTT, right? And that's why it makes it so powerful. So you can run sensors or devices in your local lab without exposing anything at all anywhere. And if you have your MQTT server, it could be a public server. The problem with the public server like this HiveMQ is that it's wide open, right? So we see that traffic to our devices, but it means that anybody else can see that traffic and they can inject messages and tweak with our devices. So what people use, they run their own MQTT servers, and there are plenty of providers that will let you do that. So you can use Amazon. There are other providers that enable you to create your MQTT instances quickly, and those instances you can protect by by logging, by password, or by TLS certificate. So, and this way you can have kind of your own private server, which you can manage, which you can use to manage your devices, right? So this is the approach which is used in production environment, right? So another question. Thanks for the webinar. It's very valuable. Please, can we get this course will be public? Yeah. So I will publish I will send the slides. I will send the references to implementation. Like you'll see, you'll see the code, all the like notes how to build it on all operating systems, on Windows, Mac, Linux, and yeah. So another thing that I will send in the email is the URL to book a one-to-one VC call with me, right? So if you have any question, if you have any project, whatever it is, which concerns like networking, like device management, over-the-air updates, MQTT, web dashboard, anything, then you can talk to me if you have like any questions. I can share anything I know with you. And there are plenty of like hidden problems, cornerstones, and so on. So you'll have this this like 101 phone call, and it's completely, it's free, no strings attached. I won't sell you anything. I won't like I will just discuss and brainstorm it, or try to answer and share my experience on any questions you might have. For you, it could be useful because you basically, I can share the experience myself and my team has. We have plenty in that specific area. And for me, it's useful because I learn what people, what like issues, what environments, what problems people are facing. So it gives me a perspective about, like real issues or potential issues that we should think about and we should address later on. So it would be useful for you and for me. So please don't hesitate to book a 101 phone call with me. So yeah, and I'm really glad that it was useful for you. Appreciate that. So Roy says serial communication can be difficult to configure and set up. I expect a mass migration to USB networking in the next couple of years. Do you agree with that statement? Well, USB is also serial, right? And specifically in this Pico device right now, you see this log, the serial log, and it's really over USB. that what it is. You can see this in this. Let me show that to you. So Mongo's examples RP2040 Pico W500. This is the build file for this firmware, and as you can see, it has these two statements like to root stdio, so all like high level printing and reading from serial functions to the USB, right? But serial, I don't think the serial will go away any soon because it's kind of like really standard, established, and relatively easy protocol to implement. Like for the microcontroller, it's way easier to implement serial other than USB. USB is a pretty complex protocol. So if you looked at the specification, if you looked at the protocol itself, it's a really complex thing. Serial, UART protocol is way less complex, right? It's also not really very simple. I think if something like that would be designed today, it would be like different, would be way simpler. And some people design really nice, simple protocols. But it was designed a long time ago when when these like hardware terminals were used, and it has a lot of legacy in it. But nevertheless, like its basic usage is pretty simple. Like just has two wires, TX/RX, like frequency settings, and pretty much it. So I think because of that, it's unlikely to go away very soon. Because if you look at the common microcontrollers, pretty much all of them, starting from the really simple 8-bit ones, they have a serial controller in. But not all of them have USB, by the way, right? So the amount of controllers with serial is, I think, considerably bigger than controllers with the built-in USB. So I'm kind of like, for the user perspective, I could maybe agree to some degree with your statement, Roy, but from the kind of like low-level hardware perspective, probably not. Like definitely USB is kind of expanding and its usage is expanding for sure. But on the for the kind of like on the low level side, the hardware side, I'm not sure the UART will go away any soon. So I hope I answered the question. So yeah, I think I have no questions anymore. So thanks a million for joining. to today's talk, and I hope that was